and welcome to all of you. And I hope everybody is fine. And we have another moment, a moment of interaction, a moment of talk, moment of exchange. And to be precise, I would like to stand my position with a very basic mathematical instrument that's used in the field of quantum mechanics. And this mathematical instrument is it's called as the wave function, and this wave function has a symbol, and this symbol is psi. So the point is that I want to deliberate the very essence of this wave function, the very importance of this wave function. And to be precise, the wave function is the basic fundamental argument that takes us to understand a system which is quantum mechanical in nature. And if we talk about the classical physics has everything to say, and it has everything to be predicted in a pure fashion. But in quantum framework, here is a tussle. Basically, there's a tussle between the deterministic nature of wave function mathematically, and then the moment you observe, you try to measure, then there is a disagreement with all other probabilities, and there is an agreement with just one probability. So if we classify the two arguments, in classical, your theory has a prediction, and the same prediction is completely calculated, it's observed once you make a measurement to that classical system. But at the same time, in quantum domain, in the quantum framework, what we have a wave function, and this wave function is completely deterministic. And when we talk about the wave function, this wave function is a mathematical argument. It encompasses the real part and the imaginary part. So the point is that here you have Schrodinger's equation, the equation that was developed by Erwin Schrödinger, and the solution of that equation is determined by using the state of the system, by using this complex wave function, which is composed of the real and imaginary part. But the point is that this mathematical argument, this wave function, is completely predictable. It's purely deterministic in the framework of theory. And the tussle only comes in action once you make the observation. And the tussle goes between all the probabilities that you predict, but once you make the measurement, you come up with just one solution. The rest of the arguments, which were purely deterministic in the framework of quantum mechanics, they all disappear, and the system reacts to your observation. So it's the observation, it's a tussle between the observation and what is to be measured. Suppose I talk about an electron. So if I have to calculate, suppose I have a particle in a box. Now this particle has a range of probabilities. So from theoretical point of view, you have this particle at all those frameworks at the same point of time. They exist there. It seems weird, but mathematically, quantum mechanically, it's all deterministic. The problem comes once you try to measure it. So making an act of measurement on the system, which is quantum mechanical in nature, what it does basically is the nature reacts to our observation, and the reaction leads to just one probability out of all the probabilities that existed in that system. So here is the core tussle is between the observation and what you are quantum mechanically predicting. And this is something that we don't understand. So there are many arguments that try to explain this tussle between the observation and the quantum mechanical deterministic approach, but you cannot take any of these things as a complete explanation of that tussle between the observation and whatever probabilities you have in front of you. And there are arguments like that come on, your system is already in those multiple states, what is taken as quantum mechanical multi-universal approach. All of the other probabilities do exist, but the system reacts only to the observation that you are making, and the things and whatever is there that you are predicting from the system. So in a very slowistic fashion, I would like to tell you that this wave function carries all information about your system, and all that information is purely deterministic in nature. And what makes things different is here your probabilities can coexist. I mean to say, if I toss a coin, it has head and tail. So you can have classical probabilities. Probability of getting head, probability of getting tail. But here in quantum mechanics, we can have both the probabilities at the same time, at the same state. I mean, your system can behave both head and tail at the same time. And if I take another example of a dice, if I throw a dice, now there are a range of probabilities. You have classical probabilities that you can calculate about this dice. But quantum mechanically, there can be a probability which encompasses all the 6 faces of that cubical box. Like the way that we have Schrödinger's cat. The cat can be in both the states. It can be dead, it can be alive. So that is a macroscopic example basically to understand the real nature of quantum mechanical particles. To be precise, the cat should be in a whole considered as a quantum mechanical particle, and then we should try to understand the Schrödinger's cat being dead and alive at the same time. So what we have wave function. This is basically the central object of the quantum mechanics. This is the original building block of the quantum mechanics. It's a vector, and it can be the part of vector space known as Hilbert's space. So what it does basically, it encodes the full information about the quantum system. It's not like that it's giving us the abstract information. It's giving us the information in terms of probabilities. No, it's giving us information completely about the system. But the problem is that it doesn't make a physical sense. You cannot have physical implications of the wave function. So what we have, it has this psi is born from Erwin Schrödinger's equation in 1926. And this wave function has revolutionized our understanding of the matter and reality at the very microscopic level. Now, what is psi? It's simply a mathematical function that describes the quantum state of the system. And what it does, it contains probabilities of all possible outcomes. All of these probabilities are deterministic from the wave function point of view, from the quantum mechanics point of view. So if we write this wave function as psi of x and t, what it means that this wave function is a function of geometry, is a function of dimensions of the system, and it's a function of time. So function of x and function of t. This wave function is a complex valued function. What it does basically, it has two parts. It has a complex part, what we call as imaginary part, and it has a real part. And as I said, this wave function has no physical interpretations. It has no physical implications. The implications exist to the probabilities, and to calculate the probabilities, you have to multiply a wave function to its complex conjugate. That's why psi square means here. If you have a wave function, suppose I choose a complex number, a plus iota b, I have to take its complex conjugate, so that will be a minus iota b. You multiply the two, you will lose the complex part of the equation. You will only come up with the number. So that's what we achieve by achieving this wave function. So once we have a wave function, once we have a solution to a differential equation that follows the basis of the quantum systems, we can calculate its probability density by simply multiplying this wave function with its complex conjugate and obtain the result. So what it does, it tells us why the particle is likely to be found. So what you do is you calculate the probabilities using psi square. And the very foundational principle of quantum mechanics, about this principle I have talked many a times, and that's what is superposition principle. As I said, superposition principle, what it does, psi allows multiple states to coexist. This is what I was saying to you. If you take a particle in a box, or if you take an example of the coin having head and tail, if you throw this coin, talking about quantum mechanical probabilities, this coin will have all probabilities. There can be a probability where the coin can have both the states, both the outcomes like head and tail. Or we can have another example of spin of the particle. You can have spin up and spin down, which makes sense when we talk about the quantum computers. So here in quantum mechanics, you can have a superposed states of these spins. So your system can be in a superposition of spin up and spin down. So this superposition that you have for these states, which is allowed by this wave function psi, it leads to the interference, and interference certainly gives you an idea of the probability of getting a maxima and probability of getting a minima, because you can have two states of interference. One is called constructive interference and another is called destructive interference. In case of constructive interference, what you have a wave, you superpose another wave, and where the waves are in same phase, you have the maximum amplitude of the wave, and where the waves are out of the phase, you are coming up with the destructive interference. Again, coming back to the measurement problem, as I said, wave function is completely deterministic. It's not anything different from that of classical mechanics from mathematical point of view, but what makes this framework a different framework is the measurement problem. Because once you measure, then you have, before the measurements, psi is spread. So you have all these probabilities for this psi. The electron is at many places at the same point of time. You have multi-universes for the same particle. And once you make an act of measurement, once you measure, what happens is there's a collapse of the wave function. The wave function collapses to a single outcome. The all other fairies of the electrons, the all other existences of the electrons, they don't come up to our observation. We come up with just one single outcome. So there's a tussle between the measurement, the act of measurement, and what you predict mathematically. So deterministic evolution versus random outcomes. So evolution of psi, as I said, it is deterministic. It's completely deterministic by Schrodinger's equation. You can predict it. You can determine all of these states. But once you have a measurement, this system takes just one state. The other states of the system, they don't respond to your measurement. Your measurement is reacted by just one act of random action of an electron. If we go back to that double-slit experiment problem, which we have discussed a couple of times in past, if you shoot one electron through the two slits, you have a double-slit experiment, you have two slits, then you have a screen, you shoot the electrons. So if I shoot one electron and I don't look at the experiment, I will observe an interference pattern on the screen. So what's happening? The electron is going through both the holes. It's going through the hole 1 and hole 2. That's why you have an interference pattern on the screen. But once I make an act of looking at my experiment, once I will look at that experiment while I'm shooting just one electron through these holes, the electron will choose either slit 1 or slit 2. So there's a problem. If you are not looking at the experiment, you have an interference pattern. But once you look at the experiment, you don't have the interference pattern is lost on the screen. So this is a tussle between the measurement and the deterministic wave function as predicted by Schrodinger's equation. Psi cannot be directly observed. So there's a problem. It's a complex function. You cannot directly observe this psi. So what we can only go with the probabilities, and probabilities will be dependent on these interference patterns. And these interference patterns have to be measurable. Once you make a measurement, you will have a complete single state of the wave function. Now, obviously, this psi is enclosing both the important natures of these quantum mechanical particles. As we describe the system, when we talk about the light, say for example, it has a dual nature. Yeah, the light particles can act as particles like photons, as confirmed by Einstein's photoelectric equation. But at the same time, this light can be treated as a wave when we have to explain the interference experiment that we perform in the laboratories. So under certain circumstances, this quantum mechanical particle is behaving completely like a wave, and some other circumstances, this wave function is behaving completely as a particle, as in the case of Planck's blackbody radiation law, or photoelectric effect, or Compton effect. These are all the effects that signify that light is basically a particle. But at the same time, the light, when you undergo the experiments of, say, the interference experiment, the double-slit experiment in a dark room, the single diffraction experiments, they give us a different detail of these photons, telling us that light is a wave. And same is the case with the microscopic particles like electrons. So this psi is taking this holistic information about the particle. It's taking account of the particle nature of the state of the system and the wave nature of the system. So what it does, this is psi. This explains us that why under certain circumstances you have a wave-like situation, and why under some other situations, as I talked about, you have a particle nature. So this is the psi that gives us the information. This information is enclosed in this complex wave function. So the psi, it can go to the atomic orbitals. In fact, you can write down the periodic table based on this wave function. And you can talk about the atomic orbitals where you have the maximum probabilities of finding the electrons in the shells of an atom as a solution to the Schrodinger's equation, because this psi can take It can take single particles, it can take multiple particles at times where you are interested. So they explain electron shells and the chemical bondings. So once you have chemical bondings, you can talk about the reactions that are taking place between different kinds of atoms. Entanglement is another important approach that is assigned with this wave function psi, and what it can do is it can describe the multiple particles together. And when you intervene a particle, this intervention of one particle will make an intervention to the rest of the particles, even if these particles are scattered, they are at the different points of the space. I mean the points where light, where you cannot have a situation that you can actually transfer information from one point to another point without simply violating the concept of speed of light, because here the impact is important. You're not actually transferring the information from one quantum mechanical particle to another, but what is happening, the act of measurement on one particle instantaneously disturbs the act of another particle. In fact, by acting on one particle at one state, you can predict what will be the outcome for another particle at another state. So entanglement shows non-local connection. So it's not like that you have the particles, they are in vicinity, so you disturb a particle, so there is a local kind of interaction between the particles that's disturbing the system. That's not the case. Here the case is non-local. I mean, your particles are at infinite distances with respect to each other. And if they are at infinite distances with respect to each other, then the act of disturbance to one particle will, if the particles are somehow entangled, so if the particles first entangle together, then you take these particles to these infinite positions, then you have, you can think of this information paradox for quantum mechanical particles. So it is purely non-local in nature. It should not be considered the way that, come on, you cannot have a particle whose speed is greater than that of speed of light. Then how is it possible for information to be transmitted from a point which is at one edge of the universe and the point which is on the another edge of the universe? So if we take the length of the virtual universe, the observable universe, it's 90 billion light years apart. So it's not a known local kind of problem. So what we are saying a particle at one edge of the observable universe and another particle at the another edge of the observable universe. So if first they are entangled, you take them to the edges, the act of disturbance on one particle will automatically lead us to the act of the disturbance of another particle. So that's what I'm telling here. Entanglement shows us the non-local connection between the particles. And you have a collapse of the wave function, and it's a key philosophical puzzle as I talked about it. So what's happening? Does collapse really happen? We're not sure about it, or is it an illusion of observation? But to be precise here, if collapse is if the collapse is completely happening, then what does that mean when we think in terms of a quantum computer? So we have a workable quantum computer in current times where this property of wave function being in multiple states at the same point of time is utilized. So it's again an all-open problem. So as I said, that your wave function has a range of probabilities. So there may be an existence of multiple universes, and this is what is called many world interpretations. So some theories suggest that psi never collapses. Instead, all outcomes occur in parallel universes. Now, is psi real or just a mathematical tool? It is a mathematical tool, but at the same time, we can calculate the probabilities and we can make an act of measurement to calculate that probability. So this is basically a philosophical debate for psi to be real or just a mathematical tool that's utilized. So we have a philosophical debate that goes on in this framework. Now, if we think in a very large sense, there are interpretations of these wave functions which connect this psi collapse with the human observations. What's that? They raise the deep questions about the mind and the matter. Maybe the mind is something that you cannot measure. This mind is enclosed of all those probabilities that are there. But once there is an act, that act gives only just one outcome. So psi inspires ideas in philosophy. It becomes a basic point in the field of philosophies, information theory, and cosmology. So it is seen as a symbol of uncertainty and potentiality. It can do a lot of work. You can reveal your systems to a very large extent using psi, and at the same time there is uncertainty as you go for the act of measurement. Quantum mechanics replaced classical determinism. So what you have here, you also have determinism in quantum mechanics, but once there is a tussle between the observation and the deterministic nature of the wave function, there is a tussle going on. The things are not completely clear in this context. So psi introduces fundamental indeterminacy. Indeterminacy, in a sense, when you talk about the observation and the deterministic outcomes of the wave function once you solve the Schrödinger's equation for a particular problem. So there are open questions. What is the ontological status of psi? So psi has to be the part of every domain of our lives as well, because psi has everything to do with the human body. Human body is made of cells, and these cells themselves are made of atoms. These atoms are made of electrons, neutrons, and protons. They are all quantum mechanical particles. So psi has everything to do with the biological life. It has everything to do with the non-biological life. So does psi represent reality, knowledge, or possibility? These are the questions that are still roaming around us. So how to interpret this wave function when you have a human body enclosing all these quantum mechanical particles which are making us in terms of these cells. So to conclude this talk, I should say psi is more than a function. As I started in the start, I said that psi is a mathematical wave function composed of the real part and the imaginary part, and it doesn't have any physical implications. But it is certainly more than that of a function. It's a bridge between mathematics, physics, and philosophy. It challenges our deepest intuitions about the nature of reality. So with this, I would like to stop this talk. Goodbye. Okay, so very good morning to all of you. And what we would like to do is we would like to continue our discussion. And we have been talking about scattering theory, and we have already obtained an equation that gives us the differential cross section. And differential cross section is d sigma by d omega. And this d sigma by d omega, I think we defined it as f of theta. Was it like that? No, okay, we didn't do that. Okay, so we had obtain the result of like d sigma by d omega is it was r square, then FL mod by n f of I. Well, this n is your number of scattering centers. And now on proceeding, if I assume that I have only one scattering center, and if I have n equal to 1 in my case, okay? So choosing one scattering center, so what will happen, you will have d sigma by d omega equals r square f of L divided by f of I. Is this clear? Yeah? Yes. Okay, this is what we had achieved in our previous discussion. And now let's move on and think about a problem. And all of you know that Schrodinger's equation that we have is valid for one particle. And we have to talk about the scattering. And for scattering, you need two particles, right? You have a particle that is acting as a probe, and this probing particle will interact with the target particle. So you have a two particle system. But your Schrodinger's equation is valid for, in the present case, for one particle. So what we can do here is, we can boil down this two body problem into a one body problem. Okay, so that will be the first case. So what we will be dealing with here is, if I assume that you have a probing particle and you have another particle, and assuming this particle to have a mass m1, this particle to have a mass m2, and if you have two particles, you can compress them into a single particle using center of mass system. So here you have two particles, and these two particles can be represented by a single particle by simply writing down the reduced mass of this system. So what will be the reduced mass? So reduced mass will be what? Let me assume that is mu, that is what? m1, m2 divided by m1 plus m2. This is point number 1. Okay? Because we have to incorporate reduced mass in Schrodinger's equation. Because we want to boil down this to a one body problem. So since you have a two particle system, right? Yes. This two particle system is boiled down to a one particle system. So you will have a collective center of mass, the mass of these two particles. So what I will do, I will assume that these two particles have a velocity. No doubt the target is at rest and your probing particle is moving. So the velocity of this combined system can be represented by VCM. Right? So if I assume that M1 has velocity V1 and M2 has velocity V2, what will be VCM? Come on. What will be VCM? VCM will be M1 V1 plus M2 V2 divided by M1 plus M2. This will give you the velocity of the center of mass of this system. But in my case, I assume that the target particle is at rest. So if the target particle is at rest, this term will immediately be equal to 0. So your VCM for the present case will be M1 V1 divided by M1 plus M2. Clear? Yes. Okay. So now what we have written down the reduced mass, and we have a problem like this. You have a particle, and this particle interacts with this particle, and you have a center of mass of this system. You have the velocity of the center of mass. So you will have scattering So you will have, say, this is R and the scattered one, this is the scattered one, and this is R dash. And I can put a third vector, and this third vector will give me, depending on the direction, this will give me R minus R dash. So this is how our problem will look like. But before moving on, what I will do is I would like to write down the Schrodinger's equation. Okay? I would like to write down it in terms of the reduced mass. So what is my Schrodinger's equation? Yeah? It is d2 psi by dx2 plus 2 mu by h cross square E minus V of x of psi of x is equal to 0. Right? Then mu is the reduced mass of the system. Okay? So what we are doing is we are compressing our problem to a one body problem. So what can I think about if I assume that, okay, this is the direction of z axis, if I choose this as z. So what you have the incident particle, and you have a particle with which this incident particle will interact, and there will be interaction and there will be scattering. Okay? Now let's go with the plane wave solution of Schrodinger's equation. So what can I do here? I will write psi, I will call it psi t, psi total. Okay? So what it will be, so you have a wave function linked with the particle that is incident with the target. So it will have a plane wave solution. The Schrodinger's equation has plane wave solution, and that solution will encompass psi incident plus psi scattered. Okay?
Yes.
Now the dependence of this solution to the Schrodinger's equation, so for the incident particle it's a plane wave, so for psi in it is e to the power of I k dot r. Alright? Plus the dependence on the scattered wave function. What is seen is that the scattered wave function is dependent on f of theta. Okay? And then you have e to the power of I k r divided by r. Okay? Now see, this is inverse relation. Okay? The potential will be 0 at infinity if you take the classical, if you take pure Coulomb approach, right? But here what is happening, the potential will become 0 at infinity means that you have a finite distance from the target. Because your target is very, very small, okay? And the length, say if my target is, say for example, 45 centimeters away from the target. This 45 centimeter is infinity with respect to the dimensions of your target. Okay? So what we say here is that the potential varies here faster than that of the normal Coulomb's approach of calculating the potential. Now another question arises, what is this f of theta? This f of theta is a constant. Now you will say, sir, whenever we write down the solution of the Schrodinger's equation, we write down it in terms of the constants.
Yes.
And why you have not incorporated a constant here? Okay. In fact, I have incorporated something like f of theta, and I define this f of theta as scattering amplitude. Now the point is, in scattering, the normalization does not play a key role. Okay? So that's why you will generally see in the books, they will not be incorporating the constants. Because you are not interested in normalization when you are discussing scattering problem. Now, is this clear?
Yes, yes.
Now, what is this f of theta? This is scattering amplitude. So it gives you the maximum magnitude of scattering. And then again you have e to the power of I k r divided by r. Now, for the situation that I talked about, I chose the direction along z. Okay? So I can think of this I k dot r. I can write down this as, so what will be psi t? It will be, it will be e to the power of I. Okay, then you have k dot xi cap plus yj cap plus zk cap. Okay, then you will have plus f of theta, which is called as scattering amplitude, divided by r e to the power of I k r. Okay, now you can see this is this k will make with z only. Okay, will it make it? So psi t can be written as e to the power of I k z plus f of theta e to the power of I k r divided by r. Okay, is it fine?
Yes.
Okay, now you understand this is psi incident. This one is what? Psi incident, and this part reflects psi scattered. Okay. Right?
Yes.
Now, we are interested in the probability density. Okay, you remember FL divided by FI. Okay, FL is linked with scattered particles and Fi is incident. So how we can calculate that? Now see, I have psi incident. Okay, I define its probability density as rho incident. And what will be that rho incident? That will be psi incident whole square. Right?
Yes, sir.
So that will be e to the power of I k z whole square. Now what does this square of the more mean? It means the complex function multiplied by its complex conjugate. So here you will get 1. So this is going to be equal to 1. Is this clear? Now I have psi scattered. What is that? That is rho scattered. And that is psi scattered whole square. So that will be f of theta. Because our problem is spherically symmetric. That's why I'm writing only theta. Otherwise, depending on the geometry of your problem, you can include the azimuthal part of scattering amplitude, f of theta and phi. So here, this is f of theta. This will be whole square divided by r square, and then e to the power of I k r whole square. What this will give us? This will give us 1. So what will be psi scattered square? Okay, this is square. That is rho scattered is, this will give us 1. This is f of theta whole square divided by r square. Right?
Yes.
Now, what we have to do is we would like to define, because we have already calculated the differential cross section, and we would like to use that for our plane wave scattering problem. And what we assume that we have a problem including a spherically symmetric situation. So you are not treating the scattering as a particle scattering, you are treating your problem as a spherically symmetric problem. That means a wavelet is coming, it is interacting with the target, and from there you are getting a spherically symmetric wavelet. Are you getting my point? So what we have? We have d sigma by d omega is, what was that? This is r square f of L divided by m is gone, f of I. Now this f of L, this f of L can be defined as rho scattered into V scattered. And Fi will be rho incident and V incident. Now the question is, what is V scattered and what is V? So V scattered is the velocity of the scattered wavelength and V incident is the velocity of the incident wavelength. Now what is assumed here in the problem is that you start with an assumption of elastic collision.
Yes.
So if your collision is elastic in nature, what is happening? There is no transfer of energy and the incident momentum is equal to the scattered momentum. So if incident momentum is equal to the scattered momentum, the incident velocity will be equal to the scattered velocity. And we can also calculate that. What will be that V incident? Okay, I think P incident. What is P? Momentum. What is that equal to? That is equal to H cross K. Are you getting my point? So what will be V incident? It will be H cross K by M. But not M, it will be mu. It cannot be M because you have a combined system. You have a reduced mass. And similarly, what about P scattered? That will be the same thing, H cross K. Are you getting? So V scattered is going to be H cross K divided by M. Okay? Now, this thing is defined and this thing is also defined and calculated. And what can I do now? I can calculate the differential cross section. Can I do that? I can do that. So what will be that? That will be d sigma by d omega is equal to r square. Okay, come on. For f of L, what is that? It is rho scattered. Okay, and V scattered. Divide by rho incident and V incident. I think these two will simply cancel. Now what about R square? R square is R square. What about rho scattered? Yeah, what was that? That was F of theta whole square divided by R square. This is it, huh?
Yes.
So R square and R square will cancel. So what is d sigma by d omega? It is F of theta whole square. Are you getting?
Yes.
So it means the differential cross section that you calculate for this particular problem is simply the square of scattering amplitude. Because f of theta is what? F of theta is scattering amplitude. It's scattering amplitude. Scattering amplitude. Okay. Is this clear?
Yes.
Now let's move on. Now see, look for the problem and look for the solution. This is our job. We are trying to find a proper solution when you choose a problem based on scattering. And what is happening? You have an incident particle. This incident particle is a plane wave and it interacts with another particle which is assumed to be a target. Okay? Now you see that you have just one target. Okay? What do you have? You have a target. And your probe is interacting with that target. It interacts with the potential of that target. Okay? And what mathematics we can think of solving this problem? You know from mathematical physics, you have a function popularly known as Green's function. And if you have a right differential operator, if you act a differential operator on the Green's function, what it leads us to? Yeah, come on. If you act on a Green's function, suppose I take the Green's function as, say, g of r and r dash, and I choose a differential operator. I choose a differential operator. What's that? Let's assume that operator is L cap. When you act this differential operator on Green's function, g r r dash, what you come up with? You come up with Dirac delta function. So this is what I'm trying to tell you basically, that when you are talking about the Green function, you are talking about the things that are happening in vicinity of that scattering. And we understand Dirac delta function. Yeah? It has a value only at x is equal to 0. Right? All other values are they are 0. So that means you can think of scattering where you have to act on the Green's function, and this Green's function will take you to that maximum amplitude. Are you getting my point? So that's an idea of Green's function. Now, if I write down Schrodinger's equation again, I would like to write down the solution of this Schrodinger's equation in terms of Green's function. Are you getting it? So what we have? We have Schrodinger's equation, and we would like to have its solution. Yeah. And I will call its solution as psi total. And what will be its solution? That will be psi incident plus psi scattered. So for psi incident, I will use e to the power of I k dot r plus, this plus is minus mu by 2 pi h cross square integral e to the power of iota k vector dot r minus r dash vector divided by r minus r dash. You have a potential V of r dash, and you have psi. I would like to write down this function as e to the power of iota k dot r dash. Right? This is the solution of Schrodinger's equation in terms of the Green's function. And it is clear that when we write down the solution in terms of the Green's function, we are localizing our problem to the point of interaction. Because if you act a differential operator on Green's function, it takes you to the Dirac delta function. Now the point is this k dot r minus r dash vector. Okay, this is a very simple problem. You can solve it. What is it? It's like you have k vector dot r vector minus r dash vector. So these are the vectors. How do you write their magnitudes? You write their magnitudes as it will be under root of k square r minus r dash times r minus r dash. Okay? Very simple product. You write it in terms of the magnitudes. When you write it in terms of magnitudes, you will have to incorporate the unit vector at some point. You will calculate this, and you will find that this k dot r minus r dash is k times magnitude of r minus r dash. Is this clear? So you are converting vector into the magnitudes. Okay, it's the same thing, 1 by r vector minus r vector dash. This you will find is equal to 1 by r. Okay, so these are the two important results that you will obtain by doing simple vector product, the dot product. Now, I would like to include this in my solution. So what's my solution? Psi t is e to the power of I k, let me write it kr, then minus mu by 2 pi h cross square, then you have integral e to the power of I k r minus r dash. I have already defined that r minus r dash. Do you remember that diagram? Okay, divide by r minus r dash. I will not write here, divide by r only. So this will be r. Then you have v of r dash. Then you have e to the power of iota kr dash. Then you will have the volume element d3x. Right? So this is how it will look like. But here you can see this psi t is e to the power of I kr minus mu by 2 pi h cross square integral e to the power of I kr e to the power of minus I kr dash. Am I right? Divide by r. Then you have v of r dash. Then e to the power of I k r dash. Then you have d3x. Clear? Yes. Now, I can get this e to the power of ikr as a magnitude outside. This r will be outside. What you are left inside is, what will be left with? You will have psi total is e to the power of ikr minus mu by 2 pi h cross square e to the power of ikr divided by r integral e to the power of minus I kr dash, then v of r dash, then e to the power of I kr dash d3x. Why am I writing x here? It has to be r. Huh? You correct it. Okay? So d3r. Okay? Now, compare this equation with that equation. What was that? Psi t was e to the power of ikz plus f of theta by r e to the power of I kr. Was it like this? Yes, sir. E to the power of I kr is here, divide by r is here, and the rest is what? F of theta. So if you compare these two equations, what will be f of theta? Can I move on? Yes. If I compare these two equations, what will be f of theta? Yeah? What will be f of theta? What is f of theta? It's the scattering amplitude. What will be this? This will be minus mu by 2 pi h cross square. Yeah? Then you will have simply the integral e to the power of minus I kr dash v of r dash e to the power of I kr dash d3r. Right? What is this? This is scattering amplitude. If you take the square of the scattering amplitude, what you will achieve? If you take the square of the scattering amplitude, what will you achieve? I will get the differential cross section. Right? So, if I scale it, what I'll get, f of theta whole square, will give me, the minus will change to plus. So you will have mu square by 4 pi square h cross 4. Then you will have integral e to the power of minus iota k r dash v of r dash e to the power of I k r dash d3r. But this is whole square. Is this clear? So I can say that the square of the scattering amplitude will give me differential cross section. So what is that? That is d sigma by d omega. So for this I will have d sigma by d omega equals the same equation. Now if I retain myself here and I can write down this integral in terms of matrix formulation. I can write down this as a matrix. So here I can say that f of theta whole square is mu square by 4 pi square h cross square psi of r dash v of r dash and psi of r dash. This whole square. Clear? So what we have? We have the scattering amplitude, right? For the present case. And what we chose?
4.
Yeah? H cross 4. Yes, this is H cross 4. It doesn't matter, basically. The constants will not change the direction of physics. Okay? So this is giving us the calculation of f of theta square. So if you want to calculate now d sigma, what will be that? That will be f of theta square d omega. Now to calculate the total integral cross section, what you will do? You will integrate this, So sigma will be integral of f of theta whole square d omega. Is this clear?
Yes.
I think. Any questions? If anybody has anything, if you want to talk about something, you can tell me. Okay, is this clear to you?
Yes.
Okay, very good morning to all of you. And we have been in the framework of quantum mechanical scattering phenomenon. And we have taken our problem to a situation where you have a probing particle. This probing particle interacts with the target, and assuming that we have one target with which the probe is interacting. In general, the problem of scattering is very complicated. It's a very complex problem to be resolved in actual mathematical framework. That's why we are looking for some plausible solutions of the problem of scattering. And Born approximation is one among them. And what is assumed in Born approximation is that you have a probing particle, okay? And this probing particle is assumed to be a wave, and this probing particle goes and interacts with the target, right? Once it interacts with the target, what is assumed here is that the spherical symmetry of the wave that interacts with the particle, which is assumed to be the target, that symmetry is not lost. But if we think in actual sense, if you have an actual problem of scattering, what's going to happen? You will have an interaction, and interaction will disturb your scattered wave. Your scattered wave will be so complicated in nature, you cannot resolve it mathematically, right? So what is the main idea here is we are taking a local interaction. The Born approximation utilizes a local interaction, and that interaction is assumed to be very vague. If we rightly go back to perturbation was something like the same. You were disturbing your system, but your system was a bound system. It was a bound system of electron and proton, say in the case of hydrogen atom. But here you are utilizing the same approach But the system is not bound, the system is unbound. You have an independent particle, you have an independent target, and there is an interaction between the two. And you are treating your problem in a similar fashion. You are treating it in a similar fashion, assuming that the scattered wave is just a perturbed wave. It can still be treated as the original wave packet of the probing particle. That's what Born approximation is. Are you getting my point? So this is how we realize the extraction of information. We extract the information about the scattering by assuming that this interaction is very weak. And we treat our problem in such a way that the scattered wave has the similar geometry, has the similar symmetry as that of the incident wave. Is this clear? So what we have psi as a total, right, of R, and what it is equal to? It is equal to psi incident plus psi scattered. Right? This is what we have, and we write down it as e to the power of I k dot R plus, here we don't have plus, we have minus mu by 2 pi h cross square, then you have integral, then you have e to the power of I will write it in vector form, k vector dot R vector minus R dash vector. And then I multiply it with the potential V of R dash. Then I will use an eigenstate psi, psi incident of R dash. And then since this is happening in a volume element, so this is D3 R dash. Fine? So this is my equation, and I would like to manipulate this equation in the framework of Born approximation. And Born approximation is telling me that your scattered wave has the same symmetry as that of the incident wave. Even though there is the difference, it introduces that part of difference, but the symmetries are same. There are other kind of disturbances which are not symmetrical in nature. All of those disturbances are avoided. These are not included in the equation. Is this clear? Okay. Now, if I look for zero order solution of this equation, zero order solution, I mean zero order wave function, zero order wave function. If I think in terms of this, in that case, the left hand side will be psi 0 of R dash. And what's the first term? That's e to the power of I k 0 dot R. See, when I introduce the zero order wave function, this function is going to be 0. Now if this is 0, this whole integral will perish. It will demolish. So you will be left with e to the power of I, but because I say 0, that means this k will be reflected by k naught. So k naught will be exclusively for the incident wave that is coming and interacting with the target. So in that case, what I'll get? I'll get this thing. So I can write down the first order equation, the first order wave function. So what will be that first order wave function now? That will be, because I will go with the first order. So what I will have psi t of R dash will be equal to, yeah? So the first term is e to the power of I k dot R, okay? That's the first term, this is the incident wave. And the second term is minus mu by 2 pi h cross square integral, right? Then what I have? E to the power of I k dot r vector minus r dash. Is this clear? Okay, maybe I forgot something. What was that? No, I forgot this is divided by r. You remember?
Yes.
We have already written down this equation in our previous lecture. So here it is divided by r. So this is divide by r. Okay, then you have v of r dash. And for psi incident r dash that I introduced in the original equation, what will be that? That will be e to the power of iota k naught r dash dot. Okay, let me use the dot. K naught r dash. Then you will have d3 r dash. Okay, right?
Yes, sir.
Let me write down this equation again. Okay, come on. What will be your psi of r dash? It will be e to the power of I k. It is not naught, it is k dot r. This is your complete incident wave. Okay? Then you have minus mu by 2 pi h cross square. And then you have an integral e to the power of I k dot r minus r dash. I'm writing it again. Divide by r. Then you have v of r dash. Then you have e to the power of e to the power of I k naught dot r dash. And then you have d3r. Fine? Okay? Now what can I do here? I can write down the same thing. E to the power of I k dot r minus mu by 2 pi h cross square. So you will have e to the power of I k dot r e to the power of minus I k dot r dash. Then you will have v of r dash. Then e to the power of I k naught dot r dash. And then you will have d3 r dash. This is divided by r. Okay? Now we can easily see that if I get this e to the power of I k dot r divided by r outside this integral, what you'll be left with? You'll be left with e to the power of I k dot r minus mu by 2 pi h cross square e to the power of I k dot r divided by r inside the integral. You will be left with e to the power of I. So this is my positive, this is my negative. So times k naught minus k r dash. Right? Okay, this is gone. And divide by r is gone. So v of r dash d3 of r dash. Is this clear?
Yes.
Yeah? Now you can see that our integral is incorporating the difference between k naught and k. And Born approximation tells us that this k naught minus k is very, very small. That's what makes it mathematically sound. That's what makes it philosophically sound. This k naught minus k. Okay? So this is my psi of r. This is psi total. Now what is your psi total as a reference? Do you remember that? Yeah, what's that? That is e to the power of I k dot r minus, no, it is plus f of. Now let's use both the angles. Okay? One is your the plane angle theta, and you have the azimuthal angle phi. So for f of theta, I'll be using f of theta and phi. Then e to the power of I k dot r divided by r. Right? And we can compare that equation with this equation. And we can write down what? The scattering amplitude. So what will be the scattering amplitude? the scattering amplitude will be, so this is my equation 2, say for example, this is my equation 1. So I will compare the two equations. You can see, when you compare the two equations, you will be leaving everything, and what you will be left with? You will be left with mu by 2 pi h cross cat, then you will be left with this integral. And that will give you what? That will give you the scattering amplitude, right? So let me go with that. So what will be that? So comparing equation 1 and 2 will give me f of theta and phi. And what this will be equal to? This will be equal to minus mu by 2 pi h cross cat. Is this clear?
Yes.
And then you will have integral, yeah, e to the power of I k naught minus k
R prime.
dot r dash divided by nothing. Then you have what?
V of R.
V of r dash
D
dq of
d3 of r.
prime.
So now what should be our next shot? The next shot should be to write down this in the spherical polar coordinates, right? Okay? To write down this in terms of the coordinates of theta and phi. So how can we write it? So this is f of theta and phi will be equal to minus mu by 2 pi h cross cat integral. I will call this e to the power of I, say for this I will use a symbol, say I will use a symbol, hey, come on, give me a symbol. For k naught minus k, let's use
X.
x, I cannot use that, may confuse us. Let me use alpha, okay, alpha, alpha dot r dash, okay. Then you will have v of r dash, and for this I have to introduce three integrals, integral 1, integral 2 and integral 3. So you have three integrals. The first integral will run from 0 to infinity, the second from 0 to pi, and the third one from 0 to 2 pi. Okay? And then what will I write? R dash cat sine theta d theta d phi. This is your integral in spherical polar coordinates. Are you getting it? So now we are talking about the scattering amplitude. And what we have done, we have made, the problem is in a very simplistic approach. Your scattered wave is not violent. Your scattered wave has a majority of its portion equivalent to the incident wave. There is a minute disturbance. There's a minute disturbance to the scattered wave. And that minute disturbance is given by alpha. And what's that alpha? So what we have basically here is you have a momentum, say h cross k naught. Okay? And you have a momentum h cross k. And you have the resultant of these two. That is what? H cross k naught minus h cross k, that we define as alpha. Isn't it? Okay? So this is momentum, this is momentum, this is momentum. I should multiply this with h cross. Right? So if I multiply this with h cross, this is also momentum. This is the resultant momentum between the two wave vectors. Okay? So what do you get from here? You get k naught minus k is alpha. Now, what is Born approximation? The Born approximation is that this alpha tends to 0. It's extremely small. Are you getting? So if alpha is tending to 0, you can approximate that this k naught is nearly equal to k. You are exploiting your integral in this framework. Are you getting?
Yes.
Okay? So let's proceed. Okay, what we have, we already have this equation, and we can take this azimuthal part out. This will give us 2 pi. Okay? So if this gives us 2 pi, this 2 pi and 2 pi will cancel. So you'll be left with minus mu by h cross square. So what I have, come on, what I have f of theta and phi, and this is minus mu by h cross square. And you have an integral from 0 to pi, and then you have an integral from 0 to infinity. Okay, then what's inside the integral?
E of I.
Yeah, it is e to the power of I alpha r cos theta, and then what you have? V of r dash, then you have r square, then you have sine theta, this is r dash square, keep this thing in mind, don't, so this is r dash square, then you have d theta and dr dash, okay, right? Okay, dr dash. I might have committed the mistake. I might have written dr here. Okay, it is dr dash because it has limits. Once you give the limits, you will incorporate that. Now the point is that you have this equation in front of you, and what can we say? We can say that this f of theta and phi will be minus mu by h cross square integral 0 to pi. Then you will have e to the power of I alpha r cosine of theta, and then sine theta d theta times integral 0 to infinity, right? I am separating the two and taking the two in a separate fashion. V of r dash and d r dash.
R square.
R square, okay, you can keep that R dash square, right? Okay, now this integral, you can use the property of elimination by substitution, and you integrate this integral. Your limits will also change once you try to solve this, and what you will obtain from this part of the integral is you will get this part of the integral, which is integral 0 to pi e to the power of I q r dash cosine theta sine theta d theta will give us 2 by q r dash. Right? So this integral will give us what? 2 by, why am I writing q here? It's alpha. It's alpha r dash. Now all I have to do is to use this result in my equation. What is my equation? F of theta and phi is minus mu by h cross square. Okay, times 2 by alpha r dash integral 0 to infinity v of r dash r dash square dr dash. This is it, right? And you can see this r dash and square will cancel. Okay, so what you are left with, minus 2 mu. I think we have boiled down it. So f of theta and phi for this situation is minus 2 mu by h cross square alpha. Alpha, you know, what's that? K naught minus k, right? Then integral 0 to infinity v of r dash multiplied by r dash and dr dash. So this is my expression that we can use to calculate this scattering cross section. But you understand the basic assumptions of the Born approximation. It is those assumptions that has led us to this equation. Now what is it? It is f of theta and phi. And if you take its square, what you will get? You will get the differential cross section. Because the differential cross section, the differential cross section is what? That is d sigma by d omega. What is that? That is f of theta and phi whole square. So the square of this, so see, you have boiled down this problem to an integral that's dependent on radius alone, right? So what will be your differential cross section? Yeah, d sigma by d omega will be, minus will convert into plus. So 2 will convert into 4 mu square by h cross raised power 4 alpha square. Then you will have integral 0 to infinity v of r dash, then you have r dash d of r dash whole square. Right?
Yes.
And from this equation, you can calculate the total scattering amplitude. You can calculate the total scattering amplitude. And you can discuss out this, you can yourself work on this equation, and you can see how it is consistent with the experimental results. And these equations are extensively used in scattering experiments that we perform in the laboratories, where you have, say, for example, if you have a particle accelerator, right? In a particle accelerator, you have an interaction. Okay, that interaction can be accounted for these kind of results that we have been obtaining. Now, particle acceleration, there's a tremendous energies are involved in particle accelerators. But when you think in terms of other interactions like X-ray diffraction, okay? So X-ray diffraction, what you do in that case? You have a crystalline solid, you allow the electromagnetic radiation, they interact with your crystal, and there again you can, this equation is very useful for the calculation of scattering amplitude or differential scattering amplitude, right? So that way, this is how Born approximation becomes essential, and it gives us the information about the system, but making sure that the scattered wavelet has maintained its symmetry with the incident wavelet that's interacting with this particle. So come on, if you have any questions, you can ask me. Yeah? No questions? So goodbye and good luck. I welcome all of you in today's interaction, and today we'll take on another framework that's used in discussing out the process of quantum mechanical scattering. But before we go into the details, into the mathematical details of partial wave analysis, I would like to describe a physical example to understand that how we make use of partial wave analysis to understand scattering, to understand the scattering between two particles. And we have a range of scatterings. We have neutron-neutron scattering. We have a scattering between a neutron and a proton. And we have X-rays as scattering. But here, the very first important thing is to realize physically that what partial wave analysis describes and what it means, at least in some fictitious physical environment that we'll be talking about. So when we say partial wave analysis, that means your whole description is based on waves. Okay? Your probing particle is a plane wave. And once this probing particle interacts with the target, you obtain a wave. Okay? And that wave is basically a disturbed wave. That is a wave which is the combination of various waves. Now, how can we demonstrate it? Now, if I take an example, suppose I take an example of a pond, okay, of a lake. I drop a pebble into the water. What will happen? You will have the waves. Okay? Now let us assume that there is a stone in this lake at infinity. So your waves that are described, that are emaniciated from this pebble, at infinity, what they will behave like? They will behave like plane waves. Right? But what's there at infinity? There's a stone. Now what will your plane wave do? It will interact with that stone. So what will you physically observe there? You will observe a glimpse of ripples. You will observe waves. You will observe waves that will originate in that stone. Around that stone, I mean to say. Are we able to connect it with the scattering? Okay, you have a plane wave, and this plane wave propagates. There's a stone, it interacts with the stone. You have a complicated description of waves around that stone. Now, the waves that will be produced around that stone, there will be some of the waves which will have spherical symmetry. And your problem is starting from a plane wave. So we must know how to write down mathematically a plane wave in terms of spherical waves. See, your problem is bound the moment this plane wave interacts with the stone. Are you getting my point? And once it interacts with the stone, assuming that you have spherical wavelets, this problem it has a coincidence with the spherical symmetry. You start with plane wave, but your target is to translate this plane wave into a spherical wave. Because once there is an interaction of the plane wave with the stone, what it does, it produces spherical harmonics. So, Schrödinger equation that we will be starting with here, it will comprise two parts. Obviously, we choose spherical symmetry in such a way that the azimuthal part of the spherical polar coordinates is taken equal to 0. So you are left with two parts. One is the radial part and another is angular part. And you have a solution for angular part and you have the solution for radial part. This is how we have to move on mathematically to understand the partial wave analysis. And this partial wave analysis it's a theoretical description of what you are doing in the laboratory. So once you perform an experiment in the laboratory, say for example, you perform an experiment in which you have low energy neutrons. You are interacting one neutron with another neutron. So you will have the experimental results. You will be calculating basically, if we go deep down to this concept, between neutrons there will be some kind of interaction. Okay? And that interaction here in quantum mechanics, we utilize it in terms of the potential. But it is the same kind of game that's happening quantum mechanically, which is like pulling one charged particle to another charged particle. The pulling may be happening somewhere in that scattering process. So what we have? We have Schrödinger's equation. Okay? So you have Schrödinger's equation. We would like to translate the plane wave solution of Schrödinger's equation in terms of to translate it into a spherical wavelet. And that spherical wavelet will compose two parts. One will be radial, another will be angular, and from angular part you will get Legendre polynomial, from radial part you will get spherical Bessel functions. And the Bessel function is spherical in nature. That's how we have to understand it. That we have been first translating a plane wave solution into a spherical solution. And then after that, we can think of scattering. So what we have? We have, if I write down Schrödinger's equation, it is del square psi plus 2 mu by h cross square. I will assume potential to be 0 here because I want a mathematical description. I want to write down my plane wave in terms of the spherical wavelets. So I will choose potential equal to 0. So here I will have E psi equals 0. So I'm choosing at the beginning this V of R is equal to 0. Right? So now you have a Laplacian operator. And you would like to write this Laplacian operator in terms of spherical polar coordinates. So if I do that, I write down this Laplacian. What will be that? That will be 1 by R square, dou by dou R of R square, dou psi by dou R. Because psi is associated with it, plus 1 by R square sine theta, dou by dou theta, then you will have sine theta, dou psi by dou theta. Right? Then plus 1 by R square sine square theta, then you will have dou 2 psi by dou phi 2. Right? Then what you will have? Plus 2 mu E by h cross square psi, and this whole thing is equal to 0. Okay? Now, the problem that we have been discussing, there is no role of azimuthal path.
Yes, it is equal to 0.
Choosing the spherical symmetry, what this part is, this part of the Laplacian operator in spherical coordinates will die. So you'll be left with first, second, and the rest of the thing. So what you are left with? You are left with 1 by R square, then dou by dou R, then you have R square, then you have dou psi by dou R, then you have plus 1 by R square sine theta, then dou by dou theta sine theta, then this is dou psi by dou theta, and so choose this theta as small theta. This is small theta. So I will put a tail. This tail is telling you that it's a small theta. And then plus k square of psi is equal to 0. This is it. Right? Now, what will be the solution of this equation? Can I solve this equation? I can't solve it because you have two unknowns of this equation. So what you do to solve this equation, when you solve the problem of hydrogen atom, what you do actually, you use an approach of variable separable approach. So for that, I will do a little bit of alignment. So what will be that alignment? Yeah? So you will have, for that, what am I going to do first is, I'm going to define this psi, which is the function of r and theta. This will be r of r and theta of theta. Now this tail is telling you that the big theta is the function of small theta. The capital R is the function of small. And you know this part, okay? You have done this part in the problem of hydrogen atom. Okay? So what we will obtain from this, when you will do that double derivatives, okay, what you will obtain? Can you tell me what you will obtain? You will obtain 1 by r of r, then d by dr of r square dr by dr, then plus 1 by theta of theta. Get it? Do you remember that? You can do it. This is d by d theta of sine theta d theta by d theta. And then you will have plus k square r. Right? This is equal to what? This is equal to 0. Now how can I solve this problem? Now I have exclusive part in terms of radius. I have an exclusive part in terms of the angle. Right? So how will I solve this problem? I will make an equation. I will choose one kind of species in one side, another kind of species on the other side. And then I will introduce a constant. So introducing a constant will lead me to the quantization. It will lead me to the solution, right? So how can I do that? So I would like to shift this part on the other side. So what you'll be left with? 1 by r of r, d by dr of r square, dr by dr, plus k square r is equal to minus 1 by theta of theta, d by d theta sine theta d theta by d theta. Alright?
Yes, sir.
Now to make the sense of this equation, otherwise it's a nonsense equation. You cannot exactly find out the things from this equation. To make this sense, what you do? You can make only sense when you will keep the left hand side to equal to some constant. And the right hand side of the same equation should be equal to the same constant. Only then this equation will make a sense. Dissolving this equation will make sense when you will introduce a constant, so that constant is equal to these parts of this equation independently. Right? So what you are going to get out of it? Okay, you know that. What is that? You have 1 by r d by dr of r square dr by dr plus k square of r equals L into L plus 1.
Yes, sir.
Right? Are you getting it? So you introduce this constant, and this constant has L in it. And this L is called orbital angular momentum quantum number. It's a quantum number. It's giving you the quantization of angular momentum. So what actually we are doing when we do partial wave analysis? We basically exploit the angular momentum of that problem. We try to understand scattering in terms of angular momentum. The angular momentum of the ripples that will form around that stone, the waves that will form around the stone with which this plane wave has interacted, right? So this will be one part of the equation. What will be another part? That will be minus 1 by theta of theta d by d theta sine theta d theta by d theta is equal to L into L plus 1. So you have these two equations. This is equation 1, say for example, say this is equation 1 and this is equation 2. Now you will have angular solution to this part of the equation. And your solution will come in terms of what? Your solution will come in terms of spherical Bessel functions. So that will have the spherical nature. And the solution of this equation will be a Legendre polynomial. Right? So what we expect from here, if I choose the angular equation, and in this angular equation I choose this theta of theta equals cosine theta. And when you solve this equation, what you get a differential equation. Oh, I should have used, I will introduce a variable. Where is the best? I will introduce a variable, say mu is equal to cos theta. So obviously you will go through all those calculations. You'll take its derivatives. You will write down cos theta in terms of sine theta. You will solve this differential equation. And what you will obtain? You will obtain a differential equation like this. 1 minus mu square d2 theta by d theta 2. Then minus 2 mu d theta by d theta. Then minus L into L plus 1 times theta of small theta is equal to 6. And the solution to this equation will be given by what? It will be given by the Legendre's polynomials. Legendre polynomials. Right? So we'll stop here. So till now, what we have tried to understand, we have tried to understand what partial wave analysis is. How we can physically understand what the problem is actually. In fact, you are dealing with particles in the laboratory. You assume that you have particles, but you treat these particles as waves. And your incident particle is treated as a plane wave. Because at infinity, in fact, if it is a wave, it will become a plane wave at infinity, right? At large distance. So this plane wave will interact with the target. And the target was the stone in the lake. And when this plane wave will interact with that stone, it will produce the spherical harmonics, right? So you are in the framework of scattering. The scattering is happening in the framework of waves. So what you are developing there, you are developing spherical harmonics, and you are trying to calculate the spherical harmonics. So when you calculate the spherical harmonics, you are calculating the angular momentum, and it is this angular momentum that becomes the basis to explain the problem of scattering. But again, I'm telling you, the approach is not exact. You are taking out. It's like, suppose in this room there's a sound, and this sound is a very bad sound. Okay? It doesn't have symmetry. It's asymmetrical in nature. Right? What am I trying to do is, I want to understand this sound. I'm trying to understand this sound, which is random in nature. It has no symmetry. So what I do, I think, come on, I will try to translate the parts of this sound into, say, for example, for the sake of understanding, the parts of this sound into a sine wave. Now what is a sine wave? Sine wave is a symmetrical wave. Okay? You know how to solve it. You know what's the answer that you're looking for. Right? So the same thing is going on here. You have scattering. You have sound. It's a bad sound. You cannot understand. You cannot explain it. But you are trying to convert the parts of this sound into symmetrical sound. You're trying to convert it into sine theta. You're trying to convert it into cosine theta. So by converting it into sine theta or cosine theta, you are getting an information about this, what should I call it? I should call it, it's a turmoil, it's a torrento, it's a very strong tide, it's a bomb at microscopic level. So that's what partial wave analysis talks about, right? So if you have any questions, you can ask me. So with this, I would like to start on partial wave analysis. A very good afternoon to all of you, and I hope everybody is fine. So the target here is that we would like to carry on our discussion on partial wave analysis, and we have undergone through the basics of this title, and we have we started by our conventional Schrödinger's equation, and we wrote down this Schrödinger's equation in spherical polar coordinates, and then we used the common variable separable approach to have equations that are independent of the other variables that are present in the equation. So what we have here is we have a situation in which we have a plane wave, a particle is presented by a plane wave, and we have been trying to write down this plane wave in terms of the superposition of the spherical wavelets. So that's the first target. Once we achieve that target, we can incorporate the potential that's existing there at the time of scattering. Now the point is that the moment there is a scattering, your system is behaving as a bound system, at least for that moment, for that state at which there is an interaction. So once we have a bound state, we can immediately think about the limits that we will be utilizing in our problem. So once you have a bound system, the limits will range from -1 to +1, and the angles that will incorporate for the particular state will run from 0 to pi. So the point is that what we have is we have those equations. We have an equation in terms of theta, and what is that equation? That is -1 by theta of theta is d theta by d theta, and then we have sine of theta, this is a small theta, then d theta by d theta, and this is equal to L times L plus 1. And this thing is already discussed because you can make these equations independent only when you incorporate a constant, and that constant is L times L plus 1, and L refers to the orbital angular momentum quantum number. So now the point is that we would like to write down this, if we symmetrize this equation, this is d theta by d theta sine, here it has to be d by d theta. Okay, so this is d by d theta, then here you have d theta by d theta. Now this theta will multiply to this, and so once it's multiplied, it will bring it back. So it was minus because if I multiply this equation with minus, so this will be minus, when it will come back, it will become plus. It's L times L plus 1 theta of theta. This is equal to 0. Now, in this equation, if we presumably assume that we introduce a variable, say mu, and assuming that this mu is equal to cos theta. So when you will use this mu equal to cos theta, you will incorporate it, you will take its derivatives, you will make the manipulations, and once you make those manipulations, what you will achieve is you will achieve the Legendre equation. And the Legendre equation that we will achieve will be 1 minus mu square times d theta by d theta. Now theta is the function of, so this is d theta by d theta, and then minus 2 mu, and it has to be the double derivative. You'll see it the moment you will incorporate that mu equal to cosine theta, you will come up with this equation, minus 2 mu d theta by d theta, and then we will have plus L times L plus 1 and theta is probably the function of mu. This is equal to 0. So this kind of Legendre differential equation will be obtained, and the solution of this equation is given by the Legendre polynomials. So the solution will come from Legendre polynomials. So let's assume that to be PL. Now PL of mu. So this is our angular part, and the next part is the radial part. So for the radial part, what we have 1 by r square d by dr of r square dr by dr. Then we have plus k square of r, and then this has to be equal to L times L plus 1. So you have another differential equation, and this differential equation is coming from the radial part of this bound system that we have at the time of interaction, at the time of scattering. So this is my differential equation. So I can think of this equation as this equation is our what we call as, this is called as so if in this equation what I do, if I come up with, say, another variable like zeta, and this zeta is equal to kr. This zeta is equal to k. See, this is r square here. So here you should not have any 1 by r square. Okay, in fact, this r square, it's 1 by r, probably. Yeah, I have committed the mistake, it's 1 by r. So once you make a transformation, what you will have r multiplied to this k square, and this r will also be multiplied to this part. So before I proceed, let me write down the equation correctly. So my equation is d by dr of r square dr by dr plus k square, then minus L times L plus 1, and these two things are multiplied by r, and this is equal to 0. This is how it looks like. So what I do, I choose another variable zeta as equal to kr. So once I do this, and I do all the calculations. In fact, you have performed all those calculations while solving the problem of hydrogen atom. The mathematical and the algebraic way is almost same. So you got to incorporate this variable in this equation. So once you incorporate this variable in this equation, what you achieve is you achieve a differential equation, a Bessel differential equation, that is d2, this is d2, yeah, so this is d2 zeta by dr2, and then you have plus, this is the result that we obtain from here, d2 zeta by dr2, and we have plus 1 plus, now it has to be, it comes out to be minus, this is 1 minus L times L plus 1 divided by zeta squared. Okay, yeah, I wrote it down in a reciprocal fashion, I think. Okay, so you are supposed to stop here. In terms of the radial part, and what we do here is we make use of another variable zeta equal to kr, and once we use this zeta into this differential equation, what we obtain is 1 by zeta square d by dr of r d, no, we change it in terms of zeta, so this is d zeta of r and d zeta by dr, then you have plus 1 minus L times L plus 1 divided by zeta squared times r. Alright, so this is what we obtain, and this is our Bessel differential equation, and the solution of Bessel differential equation leads us to Bessel spherical harmonics. Now the point is that once we achieve this equation has a solution, and the solution will be given in terms of the Bessel functions. And if I represent these Bessel functions by JL. Now this JL is a function of zeta. So once we have this thing, the overall solution at the moment of interaction, because at the moment of the interaction, the system is momentarily treated as a bound system. And when you treat it as a bound system, then your plane wave can be written as the combination of Legendre polynomials and the Bessel functions. So I can say the wave function psi, if I start with the wave function psi, this psi will lead us, what it is, because we are talking about the plane waves, e to the power of k dot r. Okay, Now how can I write this? I can write it as the superposition of, I will use a constant, a coefficient, say AL. It will be the combination of JL of zeta and PL of mu. So what we are trying here up till now is we are basically trying to mathematically translate our plane wave solution into something that's made of the superposition of the spherical wavelets. So in order to move onwards from here, see, I have taken off a range of algebraical calculations because you have done those calculations, how you use the solution of the differential equation by putting a new variable and defining a new variable and obtaining the equation in terms of this new variable. So these things are already known to us. We have already gone through this in our previous courses. So if I think about this e to the power of I k dot r, this is e to the power of, because I want to calculate the value of AL. Again, we will not use the complete mathematical formalism here because we have already done these things in mathematical physics where we have comprehensively discussed the Legendre differential equations and Bessel differential equations, their solutions, and the very important condition that's linked with Bessel functions, that is orthonormality. All of these things are done, and you can do these things as a homework in order to obtain the results that we have been using here. So here, what I'll have is, I can write this as e to the power of I k r cos theta. Okay, so this thing is equal to sigma AL JL of zeta and PL of mu. Now we can see this cos theta, we had assumed that mu is equal to cos theta. This was the first thing. So if I do that, and for kr I will use zeta. So I will have e to the power of I zeta. For cos theta I'll be using mu. This e to the power of I zeta mu will be equal to sigma AL JL of zeta and PL of mu. Now the point is that the target is basically to calculate this coefficient AL, and how we can do that? We can do that by introducing another function. Say if you will use instead of PL, you will use PM, and you will multiply by this PM on both sides of this equation. And you will integrate this equation from -1 to +1, and here you will have PM and e to the power of I zeta mu and d mu, and this will be equal to sigma. So what I'll do here is I'll get this JL of zeta, PL of mu, I'll get this out, so JL of zeta, and I will have integral -1 to +1. I'll have PL of mu and PM of mu and d mu. Now you better understand that how to solve this problem. You can solve this exactly the way we solve the problem of the problems of Legendre and Bessel equations. So So here what we do is we exploit the orthonormality property of these polynomials, and by doing so what we do is we have an integration. In the right hand side we are in the same way, but in the left hand side once we operate the integration on these two functions, what we do is we come up with the first part and the second part. Exactly what we are doing here is we are using the UV rule of integration. So once you use the UV rule of integration in the left hand side of this equation, the second term that comes in this equation, that term vanishes, because in that term what we see this the dependence comes out to be inversely proportional to zeta squared. So the second term of that integration will vanish, and finally your target is basically AL. And finally you are able to calculate this AL. And how much this AL comes? The AL, the coefficient that we obtain here, this comes out to be I raised power L times 2L plus 1. So you will go through all this crazy mathematics, because it's not crazy, it's very simple, but it will give you a target. At the middle of the problem, you will try to go on to reach to the next level, so that you're able to revise the concept. So AL will come out to be equal to this. So what can I write for the psi? What is psi then? I can write down this psi as sigma. For AL, I'll be writing I raised power L times 2L plus 1. Then I have JL of zeta, and I have PL of male. So what is happening basically? What we have done till now, we have represented the plane wave. What was that plane wave? That plane wave was e to the power of I k dot r. And we have written down this plane wave as a superposition of these wavelets as an equivalent mathematical model for a plane wave. That means you can write down a plane wave as a superposition of spherical wavelets, and that description is this, letting us realize that a plane wave is a superposition of the spherical wavelets. And certainly we can see that these wavelets are a result of there is every time the involvement of the orbital quantum number and the solution to the Bessel equation and the solution to the Legender's equation. So this is giving us a mathematical structure of a plane wave in terms of a spherical wave. Now the next point is to incorporate the actual potential. Now what we will do is we will incorporate the actual potential to the given problem. So the potential that we have, and we can look for that potential, and we can incorporate that potential in the Schrödinger's equation. But at least at this stage, we are in a position to realize that a plane wave is equivalent to a combination, to a vectorial combination of spherical wavelets. So we will start here, and in the next class we will proceed for what is left in this topic. Let's continue our discussion on partial wave analysis of Scattering problem, and I'm deliberately putting some of the missing links in my discussions, so that you're able to fill those gaps so that you can certainly have some kind of exercise that you can try to connect the two missing links between the two results that I have been putting on, because that's another way of actually generating the interest of the student, because once you lead from one step to another step, you feel pleasure in that. So there is a deliberation of that, and where we have reached in partial wave analysis, we have written down the plane wave solution as superposition of infinite number of waves, and what we have come on. So what we have is we have the wave function, we have the solution psi of r as sigma 2l plus 1 I raised power l times jl of zeta, and then pl of cosine theta, because this cosine theta is equal to mu. Now, what we can think of from here is we would like to introduce the potential to the problem with the spherical symmetry, and talking about JL of zeta, and this solution should be taken in an asymptotic fashion, so that this zeta that we have, this zeta tends to 0, this JL of zeta that we obtain, I would like to write down the final result that we will obtain. That would be like e to the power of, it will be 1 by 2 iota zeta times e to the power of I zeta minus e to the power of minus I zeta. So if I do this, I can incorporate the result for the Bessel functions that we have, which are spherically symmetric superposition of infinite number of waves. What we will have for psi of r, we can think like sigma, then we'll have 2l plus 1, we'll have 2i k of r, because we know that zeta is taken as equal to k of r, and then you will have e to the power of I k of r minus e to the power of minus k of r, and then you will have the Legendre polynomial PL cosine theta. So now, at the same time, what we have been trying to do is we are trying to incorporate the scattering. And for scattering, when we will incorporate the scattering in this problem, there will be a modified Schrödinger's equation. And how would that equation look like? That equation will look like del square psi of r, then you will have plus k square, and then you will have plus, let me choose u of r, and this will be multiplied by psi of r. Okay, where the potential that we are introducing at the moment of scattering is u of r, and how this u of r looks like. This u of r is 2 mu by h cross square v of r. And at the same time, we should think in terms of that asymptotic solution, that if r tends to infinity, that implies V of R will be equal to 0. This is a necessary mathematical condition that we have been trying to exploit for the given problem. So this is U of R, and the solution to this differential equation, which is incorporating the potential energy between the probe and the target as U of R, the solution for this can be thought of as psi of R is sigma 2L plus 1 I raised power L. Then you will have U L of R divided by R, and then PL cosine of theta. So when we use, no, it has to be UL of R. Sorry. So this has to be UL of R. So if this is the solution chosen for the overall differential equation that we have, where we have incorporated the potential, and the nature of that potential is spherically symmetric in nature, and we have been dealing with the problem of reduced mass, so that this U of R is 2 mu by h cross square V of R. And writing down the solution for this differential equation. So when we incorporate this solution in the differential equation, in Schrodinger's equation, what we do is we are able to write down that equation in terms of UL. So what we'll have d2 UL of R divided by dr2, then you'll have plus k square, and then there will be minus U of R and minus L times L plus 1 by R square, and then UL of R. So this missing link has to be achieved. You have to work on this problem to reach out from the solution that I have written for the given problem, and then you have to obtain this differential equation. So you have this differential equation in terms of UL of R. And what we can think of now is you have a differential equation, and this equation has a solution, and the solution that I started with, that was UL of R, is sigma 2L plus 1 by 2I K of R, and you will have you will have UL of R divided by R PL of cosine theta. So we have already had a situation in which we define the wave function, the total wave, the total solution to our problem as psi incident plus psi scattered. And the psi of R is, for psi incident, you have e to the power of I k dot R, and you can choose it as kz if you assume your direction along the z, and plus f of theta e to the power of I k dot R. So we can compare this this total solution. We can compare it with the psi of R that we have. And what is that? For us, we have the incident state is sigma 2L plus 1 by twice I k of R, and then you have J L of k of R and PL of cosine theta. Then plus you have f of theta then you have e to the power of I k dot r. Now this f of theta part, I should write down this as psi. Okay, I should not use it that way. I've done it wrong here. I'll be using the original thing that we have obtained. So then what we will have for the scattered part. So you will have psi of r is sigma 2l plus 1 by 2i k of r, I raised power l, j l of zeta, pl of mu, because mu is cos theta, and then for interscattering part you will have sigma 2l plus 1 by twice I k of r, and you will have I raised power l, and inside you have e to the power of I k of r minus e to the power of minus I k of r, and you can even bring this r here, and you can write down this r here, and then you have pl of mu. And you can further boil down this result, so you will have psi of r is equal to, say, this thing is over psi incident plus, you can further boil down this as sigma 2l plus 1 by 2i k, and here you will obtain, when you boil down this, obviously you will get something sine of kr minus L pi by 2 plus delta L. So when you boil down these exponentials, you will reach out to this result, and then you will multiply this by PL cosine of theta. So now this result can be compared with the result that we know, and what that result is, psi of r is this part plus f of theta. This f of theta is the scattering amplitude, and this e to the power of I dot k dot r divided by r. Now if you compare the two equations, for f of theta, what you will get, for f of theta you will be getting the scattering amplitude. So comparing the two will lead us, f of theta is equal to sigma 2l plus 1 I raised power l. You can do a simple algebra to make the reconciliation of the constants here. So that's your job, that you have to reconcile the constants. Divide by twice iota k and times sine of kr minus L pi by 2. This L pi by 2 has been also introduced here to get some kind of mathematical simplification. But what is important here is this introduction of delta L, because delta L is giving us the phase shift. And then you have your Legendre polynomial PL of cosine theta. Okay, so this delta L that is existing inside this whole crazy mathematical formulation is something which we are in need, because this delta L is letting us understand that there are phase shifters at the moment of interaction. Once your plane wave interacts with that stone, you have a range of spherical harmonics, and these harmonics are developing across along the edges of that stone, but they certainly will have the phase differences. So to incorporate those phase differences, because then you can think of the constructive and destructive interferences, that phase difference is to be introduced here as delta L. So f of theta this is the f of theta that gives us the measure of the scattering amplitude, which is a result of superposition, where you have the wavelets who have the phase differences. So these phase differences will take us from constructive interference point to the destructive interference point, where you can have the measurements of those spherical harmonics. And these spherical harmonics, the responsibility of measuring these spherical harmonics is given to the Bessel function. So if this is f of theta, which is called as scattering amplitude, we can immediately think about the differential scattering cross section. The differential scattering cross section. And what is differential scattering cross section? That is d sigma by d omega, and that is equal to f of theta whole square. So when you take the square of f of theta, you will be able to calculate the differential cross section. So to calculate the differential cross section, what we need then, we will have d sigma by d omega will be equal to, let's take the mod, you have the sigma, then you have 2l plus 1, you have I raised power l divided by 2i of k, and then you have sine of kr minus pi l by 2, then plus delta l, and then this whole thing multiplied by the Legendre polynomial PL of cos theta. And what we have to do is we have to take its square. And if we want to calculate the total cross section, if we want to calculate that, for that will be given by sigma is integral of f of theta whole square d omega. So what we can do is we can incorporate f of theta square that's here, we can incorporate that in this equation, and we will be calculating the total cross section at the moment of interaction between a plane wave and the target, and such calculations can be carried out, and this equation will give us the measure of that interaction, that short interaction between the incident plane wave and the spherical wavelets that are developed at the time of scattering. So with this, I would like to stop here, and I want you to carry on this exercise, so that you can basically, you should be able to reach the results that I have shown here. You should be able to reach out those results using the different paths, because that's what makes physics beautiful. That's what makes physics astonishing. So you should try to reach out all of those missing links that I have deliberately incorporated in this conversation. So with this, I would like to say you goodbye and have a nice time.